Alright, so problem 90 asks a lot of things actually, but the first thing, is this that one? It is, okay. So the first thing it says is you have a rubber band with the force exerted on both ends of the rubber band, so just a force exerted on the rubber band, and it gives you a graph for the force of the rubber band. That's actually not that important for this one, but more importantly it gives you the equation of F equals 33.55x to the 0.4871 equals the force for distance, and that's in newtons per end meters. And then for the first part, for A, it asks you, does the rubber band obey Hooke's law in the range shown by the graph? So again, the graph is that curve there. It's kind of a root function almost, and the answer is no, because Hooke's law is K, or force, equals K, which is your spring constant, times X, which is your distance traveled. And that is a linear function, which means it would produce a line of some varying slope, but it's going to be a straight line, and that's not a straight line. So the answer is no. And that is why. So then for part B, it goes ahead and says some more things. It says the stiffness of springs that do obey the law are measured by the value of its force constant, and then K equals F over X, which you can get this by dividing this original equation by, what is that, by X, and then you get F over X equals to K, because those two would cancel out there, and or at least on this side, so you'd still have the F over X there. And then it says that you can also write K as the change in F over the change, or the change in F over the change in X, or you can write K as K equals dF dx, which in a normal equation situation, so if we were to get rid of this, and you were to take the derivative of this in respect to X, you just end up with K, which is dF dx. So that makes sense. So then it asks us to find that in regards to this one. So our equation is up here, and since this isn't an even power, it doesn't actually change anything, sort of. So what you'll end up doing to take the derivative here, make my X a little better, so you'll bring this number here down, multiply it with whatever is out front here, and then subtract 1 from this number. So that is 0.4871, that's a terrible 8, this is K, of course, multiplied by 33.55x, and then if you subtract 1 from this, it comes out to be negative 0.5129. And that's K. So that's that part for B. I don't think it asks anything else. Oh no, it does. So then it asks, does the stiffness of this band is measured by K effective? So this is K effective. It's K. Does it increase or decrease as X is increased within this data? So an easy way to tell that, all of this stuff here is just a constant, so we can ignore it because that's going to stay the same no matter what X is. And then this part here you can rewrite it because it's to the negative exponent. You can write it as 1 over X to the 0.5129. And so as X gets bigger, this is going to get bigger, which means you have a bigger number on the bottom, which means it's going to be getting smaller. Because if you have like 1 over 10 and then 1 over 100, the number in the bottom is bigger on this one, but it's smaller. So as the number gets bigger on the bottom, it'll get smaller overall. So yeah, this is decreasing overall. I'm not going to write that up there because it's hard to write like this. So that is part B. And then for part C, it asks you how much work needs to be done to stretch the rubber band from X equals 0 to X equals 0.04 meters. Let me make sure I did this right in my notes real quick. And looks like I didn't, but that's okay because we can just do this again. Okay, so to 0.04 meters. So work equals the integral of force in regards to distance. So F dx, where, yeah, so basically we take our force equation, which is up here, this guy right there, and we take the integral in regards to x. So your work is going to equal the integral of this. So the way to do this is you add 1 to this and divide it by whatever this ends up being. So this is going to be x to the 1.4871. Adding 1's a lot easier than subtracting 1, and then this is going to be 33.55 because that stays the same, and then that will all be over 1.4871 because that's our number up there. So the idea is, again, that when you take the derivative of this, you subtract 1 from this and bring that number down. So that number, when you bring it down, will cancel out with this one, and you'll end up with what we started up there. So, yeah. I'm going to leave that because we need this part there, but the rest we don't need so much. So this is what it equals, and then you evaluate that from 0 to 0.04 meters because that's what it asks. I'm just going to do that on my calculator because I don't particularly want to do that by hand. So, really quickly, so you have 33.55 divided by 1.4871. I'm just going to store that so I can use that again. And then that is multiplied by 0.04 to the 1.4871 power. So that comes out to be 0.188. And that's going to be in joules because it's work done. Boom. So again with this, when you're evaluating an integral, it's final minus initial. Initial is just going to be 0 because if you put this to 0 here, that's just going to be, it's going to be 0. So that is our answer for that part. And then it also asks us if it's from 0.04 to 0.08 meters, what that comes out to be. So we just switch this over here to 0.04 and 0.08. And so basically we can just do that same equation again, except switch the 0.4 for 0.08, or the 0.04 for 0.08. So that comes out to be 1.4871. And that comes out to be 0.5274. So 0.527. And that equals 0.527.